Yeah, there's only 2 of us left, but share screen. We've always been all PhDs and all teachers. All right, and I'm going to mute these guys. All right, so this should do it. So we're down to first cahoots about DES, and then a little more binary kind of math. All right, so this thing is set correctly, classic. Okay, 962.038. There's stupid one time, so have to change that name. Well, there were 19 or 20 before. I'll wait a few more seconds. See if there's some people that didn't fall asleep yet. All right, 5 more seconds. Guess that's it. Okay. 6 questions. Okay, which system encrypts only half the data in each round? I did a CTF, and it was very obvious that the people that wrote that CTF had been through this book. Anyway, all right. So that's Feistel network. Okay. How many round keys does DES use? Okay, 16. What operation rearranges bits without changing them? Okay, that is permutation. Permutation is just moving them around. All right. What's the weakest part of DES? Key length is the only problem. All the rest of that stuff is really fine. Even that crazy sounding Feistel network, which sounds pretty weak, turns out to be perfectly fine. The only problem is the key length. All right. Who built Deep Crack? Yes, they did. Absolutely. You can tell open source people, they're always like frivolous and making jokes about everything. That's how you advertise that you don't work for a corporation and you don't have to wear a tie. You can give your thing stupid names. So that's EFF, Electronic Frontier Foundation in San Francisco. So what's the system with 1 56-bit key and 2 64-bit keys? This was on the slide, but I forgot to mention it. We'll see who's really awake. That's DesX. DesX is the system where you add key whitening. 2 64-bit keys. All right. So I'll record this. DH is now 2. Ziggy and Blaine are winners. All right. So now I got a couple other things to show you. The first thing is I want to talk about XOR. But before I talk about XOR, I better make sure you know your nibbles. So I'm going to repeat the nibbles. Hopefully you guys remember your nibbles. So here's the game of nibbles. In base 10, you have 147. The number on the left is the number of hundreds. The 4 is the number of tens. And the 7 is the number of ones. And that's how base 10 works. But in base 2, you only have 0 and 1. So the number on the right is the number of ones. The next number to the left is the number of 2s. The next one is the number of 4s. And if you're going to do nibbles, there's only 4 bits in a nibble. So you can count to 7 with 3 bits. 111 is 7, 110 is 6, 101 is 5, because it's 1, 4, no 2s, and 1, 1. And there is a nibble. 1s, 2s, 4s, and 8s is all you have. And so you can count to 15 by nibbles. All 1s is 15, 1010 is 10, 1001 is 9, because it's 8 plus 1, 1000 is 8, and so on. So you should know how to convert numbers from 0 to 15 in base 10 to binary. All right. So I'm just going to do the Kahoot on nibbles and make sure you guys have got that, and then we'll do XOR. So my nibbles, there they are, nibbles. All right. We'll see if this is easy for you. I'm hoping it will be. $387,062. All right, there they come. All right, I guess I'll wait another 5 seconds, see who we got. All right. So, what's 0011 in base 10? Okay, it's 3. 0B is the Python prefix to tell you this is binary. So it's not 11, it's 11 base 2. All right. Whoa, somebody really has quite a name there. If that person wins, they're going to tell me who they are. That looks like a nose. Anyway, all right. How about this one? 1111. I guess there's some way to put in Chinese for your name. Okay, that's 15, of course. How about that one? 1010. Okay, that's 10. Good. How about 7 in base 2? All right, 111. All right, how about 6? Man, serious wind out there. All right, 110. All right, 4 and 2 and no 1s. How about 14 in base 2? Okay, that is 1110. All right, now I think there's 2 more. All right, 1001 in decimal. All right, that's 9. Good. And that one, 12 in binary. Okay, 1100. 8 plus 4. All right. So let me just record this. Holy cow. All right. Swede. Ziggy times 2. And that very strange one, it looks like Chinese one, they're going to have to tell me who they are. Japanese? Okay, good. Can you read it? Okay, but I sure can't read it. But there's nobody else with a name even close. So, all right. So there's one more thing I want to talk about, which is XOR. So XOR is just another one of these bit things. You see, it's at the heart of all these crypto systems. You all use XOR one way or another. It's the cat's meow for cryptography. XOR by itself is not strong encryption, but it's part of strong encryption routines. And here's how it works. 0 exclusive OR 0 is 0, and 1 exclusive OR 1 is 0. If the 2 bits are different, the answer is 1. 1 XOR 0 or 0 XOR 1 is 1. If the 2 bits are the same, the answer is 0. So you can see from the truth table that if I feed in an equal number of zeros and ones for both of the inputs, I'll get an equal number of zeros and ones on the output. And that is super important for encryption. That's if you had something that changed the percentage of ones and zeros to something other than 50%, it would destroy information. That's because 50% ones and 50% zeros has the maximum amount of information. It has the highest entropy. This is what Claude Shannon figured out. The statistical concept of entropy is related to information. So if you have something like a Microsoft Word document, which is all full of regions that are all 0, which it is, that is a low entropy system. That is a system that doesn't contain much information. And that's why you can zip it with something like WinZip and it will get smaller because there are regions of it that are all the same that could be compressed. But if you have something compressed like a JPEG image and you zip it, it doesn't get any smaller because it has the maximum amount of information already. And there is no way to cram more information in there. And that's what you've got here. If you have an equal number of ones and zeros, you've got the maximum amount of information, the maximum amount of disorder. Anyway, so in Python, you use this caret for XOR. So there's XORing 1 bit, 0 or 0, 0, 1, 1 or 0, 1 or 1, you get 0, 1, 1, 0. And you can do 2 bits. If you do 2 bits, you just XOR them 1 by 1. So the left 0 XOR the left 0 is 0, the right 0 XOR the right 0 is 0, and so on. 0, 0 XOR 0, 1 gives you 0, 1. 0, 1 XOR 11 gives you 1, 0, because the left bits are different, so it's 1. The right bits are the same, so it's 0. XOR actually acts on only 1 bit at a time, but you can do as many bits as you like. Conceptually, you can do 8 bits, 16, 64, but you just do the bits 1 by 1. And there is no carry or anything where the result of 1 bit would affect the next bit. Each bit is just completely independent. So there's 2 bits in Python. 0, 0 XOR 1, 0 gives you a result of 1, 0, which Python writes as 2. So you might want to put it in binary instead, and then it's more easy to read. 0, 0, 1, 0 turns into 1, 0. And you can have 4 bits. So 0, 0, 0, 0 XOR 1, 0, 0, 0 gives you 1, 0, 0, 0, because the left bit had a 0 and a 1, and all the rest were zeros. This one here, 1, 1, 1, 1 XOR 1, 1, 1, 0 gives you 0, 0, 0, 1. Second from the bottom, because the left 3 bits are 1 on the left and the right, so you get 0. The last bit is different. You have a 1 and a 0, so you get a 1. So that's how it looks in Python. And I got a Kahoot about it. Feeling you might have seen this before, but even so, I don't really care. Make sure you're good at it. I don't think I need to repeat any of the other ones I've done today. As far as my XOR, there's XOR, good. All right. So let's see if you can do it. Or set. All right. This is the last thing we're going to do today. All right. 880-176. Come to people. Good. It's got a different Japanese name now, just to keep me guessing. Anyway, all right. All right. I wait 5 more seconds. Looks like 18 is the number. Okay. So 1 XOR 1. Okay, that's 0. Good. 0 XOR 1. Ooh, there come the answers. There you go. That's 1. Good. That's what I want to see. People know it. All right. 1, 1 XOR 0, 1. All right, and that's 1, 0. 1, 1 XOR 0, 1 turns into 1, 0. All right. How about 1, 1, 1, 1 to 0, 1, 1, 1? All right, good, 1,000, because the right 3 bits match. It's only the left bit that's different. All right, how about this one? 1101 XOR 0. All right, stays unchanged. XORing with 0 does nothing. All right, 1101 XOR 0110. All right, and that's it, 1011. Everything is different except the second bit that matches. All right, good. Thank you, folks who got it. NH, I thought NH, yeah, NH is now 3. And sad, and a different strange Japanese character. So, all right, that's it. I'm going to go to the lab and help anybody that needs help. And if you won, you ought to let me know who you are. You're not going to get your points. I'm going to stop the share and go to the lab.